Good afternoon, everyone. Welcome to the last talk this afternoon. As Giorgio said, my name is Tim Kothe. I'm working in the AIT, Austrian Institute of Technology, based in Vienna, headquarters in Vienna, in the unit of molecular diagnostics, and there in the group led by Hainberger, Diagnostic Biosensors. And I'm also a member of the consortium of the Horizon 2020 funded project Impetus. It is funded with about 6 million euros and will end in October this year. This project is coordinated by the AIT and is comprised in 40 partners in Austria, Belgium, Germany, and the United Kingdom. And the bigger aim of the Impetus project is to combine printing, microchip and paper technology to realize the fabrication pipeline in industrial environment. Here you can see a photo of the right now existing pilot line. It's based in Upper Austria. And some examples of the components we integrate into that pilot line. But I meant to talk about more of printing technologies. So we are integrating screen printing, flexo printing, and especially Bio-Inkjet-Printing in this case. But also we have implemented the chip mounting module and the several drying processes for sure. To end up in a seamless roll-to-roll process, which is meant to be pretty useful for a high throughput fabrication process. And it is, because of the different modules, pretty adaptable for several various sensing applications. And we would like to give access to third parties who are interested after the project and to the pilot. That's a pretty important point, I guess. And this pilot line right now should be capable of manufacturing fully integrated paper-based biosensors, which can be read out electrochemically. And when we have the results of the bioassay, this is transferred to a user smartphone by the technology. And these biosensors are meant to be self-powered, they are disposable. They are in the size of a credit card. Lateral flow testing is implemented. We have small sample volumes and fast time to result. As I already mentioned, the quantitative electrochemical readout will be implemented. And we don't need an extra readout device as we can use the smartphone at the end. And as a showcase here in the Impetus project, we will discriminate between the viral and bacterial infection. So I would like to give you more insight in that electrochemical flow testing, lateral flow testing, sorry. So as I told you, the test will be in the size of a credit card, and the lateral flow testing will happen here in the orange box, let's say. And the configuration of the lateral flow device is like shown here in the top side view. So we need something like a detection molecule that is based on a certain area, and we need something like a capture molecule. And in this experimental setup, we are placing a set of electrodes from externally. Yeah, so we have here screen printed electrodes on a, let's say, polymer substrate, and it's placed directly on top of that capture zone, let's say. And the lateral flow testing procedure is as follows. So we are applying a sample which contains the analyte of interest. And this analyte is first detected by a detection molecule. And because of the flow of the liquid through the matrix of that test, everything is carried through the matrix. until it is captured here in the capture zone, where only molecules are captured made of the analyte and the detection molecule. And here also electrochemical signal is generated, what is then captured by the electrode directly placed on top of that area. We are looking for the testing for two different analytes of interest. One is an acute phase protein, a large one, and the other one is a low molecular weight messenger molecule. It's a really small one. Okay, first of all, to make something printable by an inkjet printing technology, we need something we call ink vehicle. And this ink vehicle needs to comply with several requirements. First of all, and that is one of the most important, I guess, it must not affect the biochemical functionality of the enzyme. That's pretty important because if that is destroyed, we will not have any signal. Another aspect is that we need to comply with technical specifications of the printer. And the third topic is the interaction with the overall system, because okay, if we generate some leakage because of that vehicle, we will not win anything. Yeah. And so this is what we did first. We tried to have a closer look on the composition or on the development of that ink vehicle to make it bio-ink vehicle. So we had directly and closer looks, especially on the interaction of the protein with the chemical compounds. Here you can see, for example, UV vis spectroscopy to have a look on the integrity of the protein. If it's damaged, we will have aggregation, for example. Then we had closer looks on the interaction of the protein and the ink vehicle in terms of the viscosity, because we need to comply with the specifications of the printer. Altogether, we improved, excluded some chemical families like alcohol, destroying proteins, and adjusted for viscosity and surface tension to map criteria, specifications for the printer. And then we hold in hand ink vehicle, what was pretty well suited for our purposes. And then we conducted the electrochemical experimentations, where we first printed the detection molecules and the capture molecules for one of the analytes of interest separately. And what we did is we just tried to adjust it more and more to get the best results. Thus, we kept the concentration of the capture molecules constant while varying the concentration of the detection molecules. This we did by varying the drop spacing. So by decreasing the drop spacing, we increased the amount of molecules we placed there. And as you can see, if we decrease the drop spacing, we increase the signal. That is for both assays the case. And then we decided, okay, for the sandwich assay, we will use a drop spacing of 40. For the distributed assay, drop spacing of 28 micrometers. And the currents luckily behaved like predicted for the specific assay format. That means for the larger molecule, we use the sandwich assay, for the smaller one, the competitive assay. So it's increasing in signal, and the other one is increasing in signal. So that's fine so far. In the second step, we combined both assays. So we printed two capture lines, one detection line comprising the detection molecules for both assay formats. Let it run, and as you can see, both in parallel were read out. Additionally, we colorized and by that visualized the assays. Analyte of interest 2, decreasing visual signal. Analyte of interest 1, increasing visual signal. So the assay format is functional. Everything is fine. The components also functional. And we were able to have a parallel electrochemical detection. This was then transferred to an industrial inkjet-printing process. We just checked for the biocompatibility toward the printed materials. We were able to show jetting performance, what was pretty suitable, and also the biofunctionality after different jetting frequencies was just stable after jetting. So that is pretty straightforward to having an industrial process at the end. To sum up everything, so we were able to develop an ink vehicle, what is quite nice and keep the functionality of our biological compounds stable. We were able to perform an inkjet process and establish an inkjet process. So far, we were able to read out electrochemically 2 analytes in parallel. And one aspect I did not emphasize so much, we also developed a suitable paper for the immunochromatographic assay we are performing. And that is a development we made during the impetus. So pretty interesting, I guess. Yeah, before I thank you, I would like to stress more. Please visit us at our booth. We are here the next 2 days and are looking forward for quite nice discussions. Thank you.